So this is going to be take 3 on limits using trig identities, which makes sense because trig identities just makes a whole big mess of things. And I know you guys are going to love this. And honestly, I think this is like the most fun part about math. You basically have these puzzle pieces right here, all these identities, and you have to just change things to make it fit a certain way so that things will work out in the end. So let's go ahead and dive right into this. So the first example, we need to find the limit as theta approaches 0 of 1 minus cosine of theta over 2 sine squared theta. So I gave you this list of identities here, and let me be a little more consistent with those parentheses. You don't really need the parentheses around the theta, but it does help to understand that it is technically a function sine of theta, theta being the input. But anyways, back to the identities, and you can see they don't use the parentheses there. And so Pythagorean identities, this is one of the main ones that we'll be using. Whenever you see sine squared, cosine squared, when a trig function is squared, probably going to end up with the Pythagorean identities. Double angle identities, that's when you see a 2x or like a 2 theta on the inside, then we're going to be using double angle identities. If you look right here, you see cosine of 2 theta, probably going to be using one of these double angle identities. Then last you have tangent is sine over cosine, cosecant is 1 over sine. You should remember those should be pretty simple. So I'm looking at this to start, and I'm thinking, okay, sine squared theta. Well, I'm looking at this, and I see sine squared theta. So I'm going to go ahead and use that Pythagorean identity. Sine squared plus cosine squared equals 1. And I'm going to solve for the sine squared by subtracting the cosine squared to the other side. So sine squared is going to equal 1 minus cosine squared. So that's what's going to get substituted in. 1 minus cosine squared, I keep highlighting sine squared, but that's going to get substituted in right there. So I'm going to put that this equals the limit as theta goes to 0 of 1 minus cosine of theta over 2 times 1 minus cosine squared theta. And so now I'm looking at this, and it's not possible for me just to cross those out because this is a cosine squared, so I can't just cancel these out. But I'm seeing difference of two squares. If you're not seeing it, let me show you what I'm talking about. So difference of two squares, I'll write it right here in blue. A squared minus b squared. This is two things being squared, and it's the difference, the subtraction sign. So that's a plus b times a minus b if you were to factor it, right? We've seen this before. X squared minus 25 factors to x plus 5 times x minus 5. X squared minus 1. Technically 1 is 1 squared, right? So that's x plus 1, x minus 1. Or you could have 4 minus x squared. That would be 4 plus x, 4 minus x. And I want to make a note, we're going to see it in the second example, that we're square rooting. And that actually shows my mistake there. That shouldn't be a 4, that should be a 2. So you square root each of these, right? Square root of 4 is 2. Square root of x squared is x. Just like the 25, square root of 25 is 5. So just so you know, you square root them. That's going to help in the next example. So on this one, let me show you how that comes into play. So we have the limit as as theta approaches 0 of 1 minus cosine theta. And then technically on the bottom, 1 minus cosine squared theta. This is difference because it's subtracting of two squares, 1 squared and cosine squared. So I could separate those out as 1 plus cosine of theta, 1 minus cosine of theta. So I'm going to go ahead and take these and cancel them out because they're the same. So I'm left with the limit as theta approaches 0 of 1. There's going to be a 1 left on top since we canceled everything on the top. 2 times 1 plus cosine theta. And it was okay to cancel the 1 minus cosine. Normally you can't cancel when there's a minus sign, but it's because this is a multiple. This right here, 1 minus cosine theta, is being multiplied to everything else. So since it's a factor, we can cancel them out. Now let's go ahead and plug in the 0. If you remember the unit circle, right here, whenever theta is 0, our cosine is 1. So we have 1 over 2 times 1 plus 1, which is 1 over 2 times 2, which is 1 over 4. And there's our answer to that one. I feel like I'm kind of leaning to the left whenever I was writing these, so let me push them to the right a little bit. Yeah, it looks good. Okay, so let's look at the next one. This one looks a little bit more complicated, but I'm seeing this double angle identity right here, cosine of 2 theta. Now I want to bring in one, probably one with a sine, just because I'm seeing that right there. So cosine of 2 theta. Let's go ahead and use the 1 minus 2 sine squared theta for that. So we'll have the limit as theta approaches negative pi over 4, 1 plus the square root of 2 sine of theta over cosine of 2 theta. Now, of course, you should be plugging in the negative pi over 4 first to see if it doesn't work. I'm assuming we get a 0 over 0, and that we're further going to have to look into this and use some of these identities. So I'm going to go ahead and substitute the cosine of 2 theta in with the, what was it again? 1 minus 2 sine squared theta. And on the top, we'll have 1 plus the square root of 2 sine of theta. And what I see right here is a difference of 2 squares. What's interesting though is 2 is not a number squared though, right? So that kind of makes things a little bit complicated, but this is a minus sign. So we could separate it by taking square root. Remember how I was saying that 4, I messed it up earlier? Square root of 4 is 2, right? So we're just going to square root the 2, and it'll work out fine. You can test it. Let me show you an example. X squared minus 2 could be x plus square root of 2, x minus square root of 2. Because if you FOIL that out, x times x is x squared, and then minus x squared of 2 plus, those just cancel each other out, and then minus square root of 2 times square root of 2 is square root of 4, which is 2, right? So what I'm going to do is I'm going to rewrite the bottom one as 1 plus, I forgot the 1, 1 plus square root of 2 sine theta, 1 minus square root of 2 sine theta. And then I can go ahead and cancel out this one, the plus case, and we're left at the bottom. One minus the square root of 2 sine theta. So plug it in, negative pi over 4 on the unit circle would be right here, and the y value would be negative square root of 2 over 2. And so remember, we're talking about square root of 2 times square root of 2, square root of 4, which just ends up being 2, right? The square roots cancel each other out. So we're going to have 1 over 1 plus, because it's a negative times a negative. And that's going to be 2 over 2, because square root of 2 times square root of 2 is 2. 1 times 2 is 2. And so that's 1/2. All right, let's go ahead and take a break and do the easy one here. So sine of 2x, we know cosine of pi over 2 is 0. So let me rewrite this as a quick one, an easy one. Such a fun assignment. So sine of 2x, I'm going to go look at our double angle formula. We only have one, right? This one here, 2 sine x cosine x. So let's try switching that out. See, this is how they all should be. Cancel out the cosine x. Limit as x approaches pi over 2 of 2 sine of x, which equals 2 times sine of pi over 2, which if you remember on the unit circles, pi over 2 would be right here. And your x value is 0, your y value is 1. So this is just going to be 2. So that's quite a simple problem. That one should be quick and easy when you run into those. Hopefully most of yours that you get are going to be like that. Let's look at the last one. This is one that kind of gave me some trouble earlier. I keep messing up every time I do this video, and then I do it on my own and it works out fine. So let me give this one more try. If I can't do it this time, then I'm just going to give up. And we're like 10 minutes in, so I'm not even sure if you're still watching this. So let's go ahead and start by, actually what I'm going to do is I'm just going to switch this tangent into a sine squared over cosine squared. And honestly, some of this stuff is just going to take trial and error. That's what happens with me. All right. So here we are. We have sine squared over cosine squared times 1 minus sine of theta. And so we got to figure this one out. So here's what I'm going to do. I'm going to take the cosine squared, put that as the denominator. I just remembered how to do it. Sometimes you just got to keep looking at these. So on the top, I'm going to have sine squared times 1 minus sine of theta. And let's just leave it that way. Sometimes you might distribute and realize you got to factor it right back, which is fine. Sometimes it's just going to take that, time and time again, just working through these. And then cosine squared, if you remember, we have sine squared theta plus cosine squared theta is 1, right? Pythagorean identity. So for our cosine, we can subtract the sine squared and get that cosine squared theta is 1 minus sine squared theta. And we can go ahead and substitute that in for cosine squared. So right here, I'm going to substitute in 1 minus sine squared theta. Which means, I still need to move this. I'm going to go ahead and use the difference of two squares on this. So I'll have 1 plus sine theta, 1 minus sine theta. And then these cancel out, 1 minus sine theta, and we're left with limit theta approaches pi over 2 of sine squared theta over 1 plus sine theta. Plug in the pi over 2, and remember, pi over 2 is right here, and so your y value is 1. So that's going to be 1 squared over 1 plus 1, which is 1/2. So this time it almost got me, but I just remember that cosine squared, we can replace it there. Do the difference of two squares, cancel it out. So that's about as hard as they get. Once again, you might have to do trial and error. You might have to try a few times till you finally get this right, just like me. And that's just how these go. That's how, your typical college math problems are going to be in the future. Maybe going pages before you get it right. But here we are. It's not too bad.